What if black holes aren't the final monsters of the universe, and everything we feared about them, their ability to crush stars, time, and swallow light, was just a shadow cast by something even more disturbing? There's a cosmic object that might be hiding behind the mask of a black hole. It doesn't explode or collapse or even let go. It just waits, still, silent and watching. The interesting part is it looks exactly like a black hole, but once you cross its edge, you don't fall into a singularity. You hit something, a boundary, a surface made of matter so strange, our current physics barely has the language to describe it. Inside, there's no infinite density, just pure vacuum energy, the same force that's tearing galaxies apart, except now, it's caged, concentrated, and instead of ending space, it bends it into a prison. This thing doesn't just pull you in, it locks you away. Forever. Your atoms, your light, even your information, stored, trapped, preserved in a structure we didn't even know could exist. And the scariest part? We might have already seen it. We might have mistaken it for a black hole. We might have been staring at them the whole time, thinking we understood what we were seeing. This is not a black hole. It's something worse. And it could change everything we know about gravity, death, and the fate of the universe. Black holes have always been the main villains of the universe, the ultimate destroyers. You've probably seen them in movies or heard about them in documentaries. Giant invisible traps that swallow stars, twist space, and slow down time like a glitch in the Matrix. Nothing escapes them. Not light, not information, not even the laws of physics. They're the places where science breaks down, where the universe throws up its hands and says, "I've got nothing." But what if we've been wrong about them this whole time? Not just slightly wrong, but completely off. What if those black holes we keep talking about aren't real? Not the way we think, at least. According to some physicists, those terrifying cosmic pits might not be the end of the story. They might not even be black holes at all. Here's the thing, no one really talks about. We've never actually seen a black hole. Not directly. We've seen their effects. We've seen stars disappear around them, gas swirling into the darkness, radiation shooting out like cosmic warning signs. But the core of a black hole, the singularity, that's just math. A guess. A terrifying broken piece of a puzzle we've never been able to solve. And when the math spits out infinity, that's not a solution. That's a red flag. That's your calculator telling you something went wrong. So some scientists started asking, what if we're chasing shadows? What if all the evidence we've collected, all the signals we've interpreted, are pointing to something even more bizarre, something that hides behind the same darkness, but plays by different rules? They gave it a name, Gravastar. It sounds like science fiction, but it's not. It's a real theory, a real possibility, a real object that might already be out there in the universe, pretending to be a black hole, but isn't. From the outside, it looks the same. Dark, silent, impossible to escape. But inside, it's something completely different. No singularity, no infinite density, no end of physics. Just a strange, eerie bubble of vacuum energy, wrapped in a shell of exotic matter, holding in something we barely understand. And here's the scariest part. If gravastars are real, it means black holes might never have existed at all. It means everything we thought we knew about death in the universe, about how stars die, how matter disappears, how time itself collapses, could be wrong. Completely, terrifyingly wrong. Because maybe these aren't the endpoints of cosmic collapse. Maybe there's something worse, something colder, something smarter, and they've been right there in front of us the whole time, wearing the mask of a black hole. And if that's true, we might not be looking at the universe's ultimate destroyers. We might be staring into its deepest secret. Black holes, as predicted by Einstein's theory of general relativity, contain something called a singularity, a place where gravity becomes infinite, space folds into itself, and time just stops. But let's be real, That sounds more like a glitch in a video game than something the universe would actually allow. Infinity isn't a real answer. It's a math error. It's what you get when your equations run off the rails and stop matching reality. And that's exactly what happens whenever we zoom in too close on a black hole. The math breaks, physics breaks, everything just falls apart, which has made scientists wonder, maybe the singularity isn't real at all. Maybe it's not some deep truth about the universe. Maybe it's just a dead end. And if that's the case, then what actually sits at the center of these cosmic monsters? Because if it's not an infinite point of destruction, it might be something way stranger. Something that pushes back instead of pulling in. Something that doesn't just break the rules, it rewrites them. And the more we look, the more it seems like black holes might be wearing a mask. And under that mask is something terrifying. The birth of a monster. Back in the early 2000s, two physicists, Pavel Mazur and Emil Motola, sat with a problem that had haunted science for decades. A problem buried deep in the heart of a black hole. They weren't trying to prove black holes didn't exist. Not at first. They were just doing what scientists do best. Asking, what if? What if black holes weren't what we thought? What if the thing we've been picturing, a place where gravity goes infinite and time rips itself apart, wasn't real? Because honestly, the idea of a singularity doesn't make any sense. Sure, the math adds up. Kind of. Einstein's equations predict it, but they also explode when you push them too far. They spit out infinities. They break down. And if your math collapses into infinity, it usually means you've stepped outside the real world. Mazur and Motola knew this. They also knew something even weirder. That quantum physics, the science of particles and probabilities, hates infinities. In the quantum world, things are supposed to be uncertain, but never infinite. That's the red line. Cross it, and reality starts falling apart. So the two of them started asking, what if nature never allows a singularity to form in the first place? What if something else happens when a star dies? Something stranger, but smarter. And that's when they came up with one of the boldest ideas in modern physics. An idea so out there, most people dismissed it as pure science fiction. But they weren't joking. They called it a Gravastar, short for gravitational vacuum star, and it might just be the most terrifying thing in the universe. Now imagine this. You're floating out in deep space. In the distance you see something dark. Not just dark, pitch black. So black that even the light around it seems to bend away. You can't see inside it. You can't scan it. You can't even escape it if you get too close. To any telescope, any observer, any camera, it looks exactly like a black hole. But here's the catch. It's not. Because if you could somehow peel back that darkness, if you could survive long enough to look inside, you wouldn't find a singularity. You wouldn't see a point of infinite density where all the rules of the universe break down. Instead, you'd find something almost peaceful, a core of vacuum energy, not a raging fireball or a crushing core, but a kind of pressure that comes from nothing. It sounds absurd, right? How can nothing push back against gravity? Well, in quantum physics, nothing isn't empty, it's alive. Even in a perfect vacuum, particles are popping in and out of existence. Fields are trembling. Space itself is buzzing with energy. This is called vacuum energy, and it might be the most misunderstood force in the cosmos. Now imagine that force, trapped inside the heart of a dying star. As the outer layers collapse inward, gravity tries to crush everything into a single point. But the vacuum fights back. It pushes out, with a negative pressure so strange that it doesn't weaken as it expands. It stays strong. And in just the right balance, something amazing happens. The collapse stops, not with a bang, not with an explosion, but with a bounce. The inward pull of gravity and the outward push of vacuum energy reach a stalemate, and that's when the shell forms. This isn't just a hard surface like a planet. This shell is made of exotic matter, a kind of material that doesn't behave like anything we know. It resists gravity in ways that normal matter can't. It bends the rules of mass, pressure, and time. It's so dense so tightly wound that not even light can get past it. From the outside, you'd never know it's there. Everything about it mimics a black hole. It bends space, warps time, even pulls in matter like its darker cousin. But once something falls in, it doesn't get destroyed. It gets trapped, pressed against the shell, and maybe, just maybe, stored forever, like data written into the fabric of space-time. To Mazur and Mottola, this wasn't just a fun theory. It was a fix, a patch for the places where general relativity and quantum mechanics just refused to get along. Instead of choosing sides between Einstein and quantum physics, the Gravastar brings them both to the table. It says, maybe we don't need to believe in singularities. Maybe nature already found a better way, a cleaner way, a more terrifying way. Because here's what makes Gravastars so scary. You can't tell when you're looking at one. Right now, the telescopes scanning the skies, the radio arrays, the X-ray detectors, the gravitational wave observatories, they're all hunting black holes. They see their effects, their collisions, their shadows. But what if some of those shadows weren't black holes at all? What if we've already seen Gravastars and we just didn't know it? What if we've been pointing our instruments at these cosmic traps, staring into their darkness, and calling them black holes simply because we had no other name? Mazur and Mottola's idea didn't stay in the back pages of physics journals. It spread, quietly, cautiously, because it doesn't just offer a new explanation. It throws a curveball at our entire view of the universe. It asks, what if death isn't the end? What if collapse doesn't lead to destruction, but to transformation? What if black holes aren't monsters, but masks? And under that mask, something even more patient, even more powerful, and maybe, just maybe, more terrifying. What is a Gravastar? Imagine this. From the outside, it looks like a black hole. Same pitch black shell, same terrifying gravity, same silence. No light, no escape. To the eye, it's identical, like a cosmic twin. But that's the trap, because inside, it's something completely different. It's not a black hole, it's an imposter, a cosmic trick, a gravitational decoy. A Gravastar is short for gravitational vacuum star, which already sounds like something ripped out of a sci-fi movie. But this isn't fiction. It's a real idea, proposed by real physicists. And if they're right, we might have misunderstood the most terrifying thing in the universe this entire time. Let's break it down. When a massive star dies, gravity takes over. It collapses inward under its own weight. According to traditional physics, there's no stopping it. The star crushes itself into a singularity, a point so dense, so heavy, that the laws of physics just stop working. That's the black hole version. Total collapse, no return. But the Gravastar story doesn't end like that. Something weirder happens. As the star begins to collapse, instead of falling forever, it hits resistance. A force pushes back, not from matter, not from heat, but from space itself. Inside the Gravastar, at its core, is nothing. Not empty space, not a vacuum like in a bottle. This is a quantum vacuum, the purest version of nothing science can describe. But in the universe, even nothing is something. Especially this nothing. Because that vacuum isn't passive, it's energetic. It's what scientists call vacuum energy. And it's the same strange force we believe is making the universe expand faster and faster. The same stuff behind dark energy. The same force that, instead of pulling things in, pushes them apart. Now picture that force trapped inside the collapsing star. Pressure builds. But this isn't the kind of pressure we're used to. This is negative pressure. It doesn't squeeze. It expands. It rebels. It fights gravity, not with brute strength, but with an eerie, silent push. It's like watching a balloon inflate against the collapse of a building. At the edge of this vacuum core, a shell forms. But not just any shell. This is exotic matter. And when physicists say exotic, they don't mean rare. They mean it doesn't follow the normal rules. This stuff bends gravity in weird ways. It has mass, but it pushes instead of pulling. It doesn't break under pressure. It thrives on it. Together, the vacuum core and the exotic shell form a perfect balance. Gravity still pulls inward, but the vacuum energy pushes outward, like two cosmic forces caught in a silent standoff. Neither wins, neither gives up. They just hold each other in place. And what forms from that is the Gravastar. It's not collapsing like a black hole, and it's not exploding like a supernova. It's stuck, trapped, balanced, suspended at the edge of destruction. And here's the terrifying part. From the outside, you'd never know. A Gravastar doesn't have an event horizon, the point of no return that defines a black hole, but it comes close, so close that light bends around it, so close that time slows near it, so close that you'd need tools far more advanced than anything we have to notice the difference. To us, it's a shadow, a ghost, a perfect disguise. But what's happening inside couldn't be more different. In a black hole, once you cross the line, it's over. You fall, forever, to a point that shouldn't exist. In a Gravastar, you'd hit the shell. You'd collide with something. You might bounce, or break apart, or be frozen in place by forces you can't see or escape. The Gravastar doesn't destroy you the way a black hole does. It doesn't crush you into oblivion. It traps you, stores you, keeps your information. Every atom, every bit of energy, every part of you gets recorded on its surface, like data burned onto a galactic hard drive. And that's not just poetic. That's a real idea in physics. That information can't be destroyed, only transformed. And Gravastars might be the perfect vaults to keep it. Think about that. All the matter that's fallen in, all the energy from stars, gas, and dust. It's still there, not gone, just locked inside the shell. Maybe forever. Some scientists believe that this shell could even pulse, vibrate, echo, that if two Gravastars collided, their quantum surfaces could ripple in ways that black holes can't, sending out faint gravitational signatures, cosmic whispers that we might have already heard. We just didn't recognize what they were. So the Gravastar isn't just a theoretical object. It's a challenge to everything we thought we knew about collapse, death, and gravity itself. It says maybe the universe doesn't crush things into points of madness. Maybe it transforms them, holds them, contains them. And if Gravastars are real, then maybe black holes aren't. Maybe what we've called black holes this whole time were something else. Maybe we've been staring into the mouths of these monsters, thinking they were the end, when really, they were just beginning. Why this changes everything. If Gravastars are real, they flip everything we thought we knew about black holes on its head. No more infinite density, no more lost information, no more math breaking down at the worst possible moment. Instead of collapsing into a point that defies physics, a Gravastar holds everything together, with dark energy pushing out and a strange shell keeping it in. It's not just cleaner math, it's a completely different way the universe could work. Gravity doesn't win, it gets balanced. And that balance, it might be the secret to everything we've been getting wrong about space, time, and what happens at the edge of forever. Let's go through a few. Problem. The singularity problem. What if the very heart of a black hole, the place where all its mass collapses, doesn't actually exist the way we think? Einstein's equations tell a shocking story. At the center of a black hole lies a singularity, a point of infinite density and zero volume. Imagine all the stars, planets, and dust that have fallen into that black hole, crushed into a space so small, it has no size at all. This singularity is like the ultimate cosmic glitch, a place where our understanding of physics simply breaks down. Space, time, and the very fabric of reality twist and warp beyond recognition. But here's the catch. Infinite density isn't just strange, it's impossible. Quantum physics, the law book for atoms and the tiniest particles, draws a hard line. It forbids infinities because they erase meaning. At the quantum level, everything has limits. Particles jitter, energies fluctuate, and uncertainty reigns supreme. The rules of quantum mechanics refuse to let matter collapse into an infinitely small point. There must be some sort of boundary, some fundamental structure, something finite. So we're caught between two cosmic titans. Einstein's gravity says infinite singularity. Quantum physics says no way. This is the infamous singularity problem, the collision of two great pillars of physics, each with an answer the other rejects. For decades, scientists have been wrestling with this contradiction. How can a black hole's core be infinitely dense, yet particles can't be squeezed infinitely? What really lurks at the center of these cosmic monsters? Enter the radical possibility of gravastars, a revolutionary idea that might just rewrite the rules of space and time. Unlike black holes with their destructive singularities, gravastars propose a finite, stable core, a cosmic heart that doesn't break the laws of physics. Picture it like this. Instead of matter collapsing endlessly into an infinitely small point, imagine it hitting a cosmic firewall, a quantum shell that pushes back, halting collapse and holding everything in delicate balance. This shell, made of exotic matter and vacuum energy, acts like an impenetrable bubble, a fortress built not from iron or stone, but from the very fabric of space-time itself. Inside this shell is no singularity, no infinite crunch. Instead, a core of vacuum energy, a strange form of energy that fills space and exerts outward pressure, holds the structure stable. It's as if the gravastar is a star's last heartbeat, frozen in time, a heartbeat made not of blood and cells, but of quantum forces and cosmic tension. This idea upends everything we thought we knew about gravity and collapse. It means the end of a star's life isn't a chaotic, crushing death into oblivion, but a transformation into something far stranger and more beautiful. Gravastars, if real, solve the paradox that has haunted physics for generations. They are a cosmic compromise, a place where gravity and quantum mechanics meet and shake hands instead of tearing each other apart. Yet, the implications go deeper. If the singularity isn't real, then what is the nature of space inside these objects? Could the universe itself be filled with these stable quantum bubbles, cosmic seeds of new physics waiting to be understood? And what about the edge, the shell? The gravastar's quantum shell is no ordinary boundary. It pulses with vacuum energy, creating a barrier that warps light, bends time, and traps gravity in ways we are only beginning to imagine. This shell is a cosmic firewall, a quantum firewall, that shields the interior from the outside universe, yet it glimmers with echoes of the star that once lived inside. We may never see the inside directly, but its presence could be inferred by the ripples it sends across space-time. Gravitational waves, echoes that whisper secrets of the gravastar's existence. Scientists have begun to wonder if some signals we've detected from black hole mergers might actually come from gravastars, shadows of these mysterious quantum structures. This possibility opens a floodgate of questions. What if every black hole we observe is actually a gravastar in disguise? What if the singularity is just a myth, a mathematical mirage born from incomplete theories? And what if the universe is far more stable, less destructive than we feared, thanks to these quantum guardians? The singularity problem isn't just a puzzle in physics textbooks. It's a cosmic crossroads, a test of our deepest theories about reality. Whether gravastars are the answer or not, the debate forces us to rethink what we know about the most extreme places in the universe. It pushes us to question the limits of gravity, the nature of quantum mechanics, and the very structure of space-time. And it leaves us with a chilling possibility. What if the terrifying singularity at the center of a black hole is nothing but an illusion? What if, instead, we're looking at the glowing shell of a gravastar, a quantum fortress standing tall against the infinite collapse, a cosmic heartbeat frozen in the dark, guarding secrets we have only begun to glimpse? The information paradox. Black holes are cosmic monsters. They pull in everything, matter, light, even information itself, dragging it past an invisible boundary known as the event horizon. Cross that line, and everything vanishes, or so we thought. Imagine throwing your most precious memories, every detail of your life, into a black hole. If the rules of classical physics held true, that information would be swallowed whole, forever lost. But here's the catch. According to the rules of quantum mechanics, information can never truly disappear. It must be preserved somewhere, somehow. This contradiction is what physicists call the information paradox. It's a riddle wrapped in the heart of the universe's most mysterious objects. So, how can black holes swallow information but never erase it? The paradox shakes the foundations of our understanding. It forces us to rethink what we know about space, time, and reality itself. But what if black holes don't actually swallow information? What if something else is happening? Something even stranger? Enter the concept of gravastars, gravitational vacuum stars. These objects could hold the key to unlocking this cosmic mystery. Gravastars, unlike black holes, don't have a singularity, a crushing point of infinite density. Instead, they have a shell made of exotic matter, a kind of quantum barrier surrounding a bubble of vacuum energy. Picture it like a cosmic shell, a shell that acts as a container for everything the gravastar swallows. Think of this shell as a cosmic hard drive, recording every speck of matter, every photon, every bit of information that tries to enter. The gravastar's shell is a place where information is not destroyed, but stored, locked away from the rest of the universe. This idea flips the narrative. Instead of losing information forever beyond the event horizon, gravastars suggest that information survives on the surface, imprinted in the very fabric of space-time itself. Now, why is this so important? Because it challenges a cornerstone of physics, the principle of unitarity, which says that information is never lost, only transformed. It's the foundation for everything quantum mechanics depends on. If information could be erased, the entire framework would crumble, and black holes, as we once thought of them, seem to break this rule. The gravastar model offers a way to keep unitarity intact. Information isn't lost, but stored in a kind of cosmic memory bank. To understand this better, imagine a hologram. A hologram is a flat surface that contains a three-dimensional image. In the same way, the gravastar's shell could act like a holographic surface, encoding the information of everything inside it, preserving all the data, even if we can't see it. Scientists call this the holographic principle, the idea that all the information contained within a volume of space can be described by data on its boundary. Gravastars embody this principle in a dramatic way. Instead of a black hole devouring information, they guard it behind a shimmering quantum shell. But what about black holes then? Are gravastars real or just theoretical? That's where things get even weirder. Recent observations, like those from the Event Horizon Telescope capturing the famous M87 star black hole shadow, give us clues, but nothing definitive. Some data fits black hole models perfectly, but some puzzling anomalies hint at the possibility of alternatives like gravastars lurking in the cosmic shadows. Scientists also detect gravitational waves, ripples in space-time from colliding massive objects, which might one day tell us if gravastars really exist. If gravastars are real, they rewrite cosmic history. They solve the paradox by replacing the dark, destructive singularity with a shell that preserves everything. Imagine a star collapsing under gravity, but stopping just short of becoming a black hole, stabilizing into a gravastar with a protective quantum shell. The collapse isn't a final surrender, it's a cosmic pause. Inside, vacuum energy pushes back, balancing the crushing pull of gravity. This balance prevents the formation of a singularity and keeps information safe. So, what does this mean for us? For decades, physicists have struggled to reconcile general relativity, the theory of gravity, and quantum mechanics, the physics of the very small. Black holes represent the ultimate battleground for these two giants. Gravastars offer a middle ground, They suggest the universe doesn't destroy information. It stores it in a cosmic archive, a shell that quietly records the story of everything it swallows. This cosmic hard drive might hold answers to mysteries we haven't even imagined. Could it mean that the universe itself is a giant quantum computer, constantly processing and preserving information? Could we one day decode the shell and read the memories of stars long gone? The idea stretches the imagination, but feels strangely plausible. Because if the universe respects quantum rules, if information can't be destroyed, then gravastars are not just science fiction. They are a lifeline for the laws of physics. But the mystery deepens. If the shell stores information, how? Is it encoded in particles, vibrations of space-time, some unknown exotic matter? And if information is never lost, does that mean black holes aren't as destructive as they seem? Could we one day find a way to retrieve lost information? These questions keep physicists awake at night. The information paradox is not just about black holes. It's about the nature of reality itself. It's a puzzle that forces us to reconsider everything, from the tiniest particles to the vast cosmos. And gravastars, with their strange quantum shells, might be the cosmic gatekeepers holding the answers. The idea that information is never lost, only transformed and stored, echoes through the universe like a hidden code waiting to be cracked. So next time you think about black holes swallowing everything, remember, maybe it's not the end. Maybe the universe writes everything down in a cosmic ledger, preserved behind a shimmering quantum shell, a place where nothing truly disappears. Because in the vast, mysterious universe, even destruction might be just another form of preservation. And that's the true heart of the information paradox. The problem of proof. What if I told you that right now, somewhere out there in the depths of space, a cosmic enigma waits silently, hiding in plain sight? A gravastar, a mysterious rival to the black hole, might be lurking, indistinguishable from the shadowy monsters we've spent decades hunting. And yet, we can't tell them apart. Look at it from a distance. A gravastar would wear the same cosmic mask as a black hole. It would bend light with a gravitational pull so intense, it warps space itself. It would drag in dust, gas, and even whole stars, creating a blazing whirlpool of matter, what we call an accretion disk. That glowing ring of destruction swirling around the darkness. A gravastar would have it too. Even our most powerful eyes on the cosmos, the Event Horizon Telescope, which made history by capturing the first ever image of a black hole's silhouette in galaxy M87 star, wouldn't know the difference. It would see the same shadow, the same bending light, the same warping of space and time. From our vantage point here on Earth, a gravastar and a black hole would be cosmic twins, impossible to tell apart. This is the problem of proof. It's the ultimate challenge in modern astrophysics. How to prove what hides beyond that event horizon? How can we say for sure whether a dark cosmic shape is a black hole, the final collapse of a dead star, or a gravastar, a quantum fortress standing tall against collapse itself? The problem cuts to the heart of everything we believe about gravity, space, and the fate of stars. Black holes are known for their singularities, points of infinite density, where the laws of physics break down. Gravastars challenge this idea by replacing that singularity with a shell of exotic matter, a thin quantum shell that acts like a cosmic firewall. Instead of matter crushing into a point, it hits a quantum pressure that stops collapse in its tracks, creating a vacuum energy core surrounded by a shimmering shell. This radical idea isn't just theoretical musing, it's backed by serious physicists, grappling with the same problems Einstein's equations pose. Yet here's the cruel irony. That quantum shell, the gravastar's secret, is also what makes it impossible to prove. Because from outside, gravity looks the same. Space bends identically. Light is trapped and curved just as fiercely. Matter is swallowed and heated in the same fiery dance. All the cosmic fireworks a black hole puts on, a gravastar mimics perfectly. So how do we break the cosmic tie? How do we tell which shadow is which when they look, act, and behave alike? The answer might lie in the ripples of space and time itself. Gravitational waves. You've heard of gravitational waves, those ripples that race across the universe after colossal cosmic collisions. The Laser Interferometer, Gravitational Wave Observatory, LIGO, caught the first of these waves in 2015, opening a new window into the universe. These waves are like the universe's whispers, carrying secrets from the darkest events billions of light years away. Black holes colliding send out a very specific gravitational song, a ringing chorus as they merge and settle, like two cosmic bells struck together, fading away in a well-known pattern called a ring down. But a gravastar might sing a different tune, because instead of matter collapsing endlessly into a singularity, the gravastar's quantum shell could echo gravitational waves differently. The shell might vibrate, pulse, or even trap waves inside like a cosmic drum, bouncing ripples back and forth in ways a black hole never could. If we could catch that echo, a faint, strange reverberation hidden in the waves, we could know we're looking at a gravastar, not a black hole. It's like trying to distinguish two identical twins by their laughter rather than their faces. But detecting these echoes isn't easy. The signals would be faint, subtle, buried deep in cosmic noise. Our current detectors need to be pushed to their limits, and even then, it's a gamble whether the universe will give us the data we crave. We're searching for a ghost song in the dark, a whisper that might never come. Yet hope remains. As our instruments grow sharper and more sensitive, the chance of hearing that echo inches closer. Future observatories, like the space-based LISA mission, aim to listen deeper, catching gravitational waves at different frequencies and distances. If they hear it, everything changes, because proving gravastars exist would rewrite our cosmic story. It would solve paradoxes that black holes have long posed, like what really happens inside the event horizon, or how information might escape destruction. It would show that quantum mechanics and gravity dance together in ways we never imagined. We discover that the universe has built in a failsafe, a cosmic firewall, guarding reality itself. But until then, the problem of proof remains the biggest mystery staring back at us from the depths of space. We are trapped in the shadow of something unseen, unable to say whether it's a bottomless pit or a brilliant quantum shell cloaked in darkness. And perhaps that is the most terrifying thought of all, that the greatest secrets of the universe might be hidden, not in distant stars, but in the silence of echoes we have yet to hear. The ghost in the gravity. What if the most gripping signals from the cosmos were not just echoes of colliding black holes, but whispers of something far stranger, something that could rewrite everything we thought we knew about the darkest objects in the universe? In 2015, a breakthrough shook the foundations of astrophysics. Scientists detected gravitational waves, ripples in the very fabric of space and time, for the first time ever. These waves were born from titanic collisions between black holes, cosmic dances so violent they sent shock waves across the universe itself. For the first time, we could listen to the music of gravity, the symphony of crashing giants billions of light years away. But amid this monumental discovery, a subtle mystery emerged, a ghost haunting the data. As researchers combed through the gravitational wave signals, they noticed something unusual. After the main crescendo of the cosmic collision faded, faint, extra ripples lingered in the aftermath. Like a distant echo, they shimmered, subtle, elusive, and unexpected. These faint aftershocks didn't fit the neat predictions of classical black hole physics. They were anomalies that whispered of something beyond the known. It was as if the universe had spoken, then paused, then whispered again. A ghostly voice layered beneath the thunder. What could cause such echoes? In the classical picture, a black hole is a cosmic pit so deep and dense that nothing can escape. Not light, not matter, not even sound or waves. When two black holes collide, they merge into a larger black hole, and the gravitational waves they create should quickly die down as the new black hole settles into its final form. Smooth, silent, and still. No ringing bells, no aftershocks, just silence. But what if that's not the whole story? Enter the Gravastar, a radical, almost science fiction-sounding idea that challenges the very nature of black holes. Imagine an object that looks like a black hole from a distance, but is fundamentally different inside. Instead of a mysterious singularity, an infinitely dense point. At its core, a gravastar has a surface, a shell of exotic matter, where the collapse of the star's core is somehow halted. This shell acts like a cosmic membrane, a boundary between the vacuum inside and the rest of the universe. This shell could ring and bounce, like the surface of a bell struck by a hammer. So, when two gravastars collide, the gravitational waves they create wouldn't just fade away quietly. Instead, the collision would send ripples bouncing off these shells, echoes, ringing vibrations, aftershocks that could linger, much like the faint extra waves seen by LIGO, the world's gravitational wave observatory. Could those faint signals already recorded be the signature of gravastars rather than black holes? Some physicists think so. They believe that the so-called echoes in the gravitational wave data are the ghostly fingerprint of gravastars, remnants of an exotic, ultra-dense shell ringing in the aftermath of a cosmic collision. This possibility doesn't just rewrite our understanding of what happens when massive stars die. It tears open new questions about the nature of space, time, and gravity itself. Because if gravastars exist, the universe might be far stranger and more complex than Einstein's black holes suggest. The echoes in gravity's song hint at a hidden structure beneath the cosmic veil, a secret realm where the rules of physics are still being rewritten. Imagine standing at the edge of a dark forest, hearing faint footsteps behind you that don't quite belong. You turn around, but see only shadows. Those shadows might be the gravastar's echoes, signals from an unknown frontier, waiting to be understood. This ghost in the gravity isn't just a scientific curiosity. It's a cosmic invitation to rethink what we believe about the universe's most extreme objects. Are we hearing the final ring of a dying black hole? Or is it the haunting song of a gravastar's surface, vibrating across space-time? Either way, these faint echoes challenge us to listen closer, to question the silence, and to embrace the cosmic mysteries that still await. Because in the vast darkness of space, the faintest whisper can change everything. What happens if you fall into one? Imagine this. You're an astronaut, alone, drifting through space. Your ship's instruments blink erratically. Ahead looms a dark silhouette, a swirling shadow that looks just like a black hole. The event horizon, a point of no return, draws you closer. Your fate seems sealed. But it's not a black hole. It's something stranger, far more mysterious. It's a gravastar. What does that mean for you? Most people imagine black holes as cosmic vacuum cleaners, swallowing everything whole, crushing and erasing it in a singularity so dense and violent, it defies all known physics. The event horizon marks the boundary where escape becomes impossible. Cross it, and you're doomed to be crushed beyond recognition. But a gravastar? That's a different beast altogether. It challenges everything we think we know about the death of stars and the destruction of matter. As you approach the gravastar, you'd expect to fall smoothly through its event horizon, a point similar to a black hole's, without any immediate physical pain. After all, in a black hole, the event horizon is a point of no return, but not necessarily a place of destruction. The true annihilation only happens deeper inside, at the singularity. But with a gravastar, the story flips. Instead of falling into empty space and spiraling toward a destructive core, you'd find yourself crashing against something. A shell. Not a solid surface like a planet, but an invisible, ultra-thin, and incredibly dense quantum shell. Think of it as a cosmic firewall, a barrier made of exotic matter, unlike anything on Earth. This shell isn't made of atoms as we know them. It's composed of energy in a state that challenges classical physics, a kind of vacuum energy holding back the collapse of what would otherwise become a black hole. This quantum shell is the Gravastars' defining feature, a boundary between the universe as you know it and an unknown interior realm where space-time itself warps and twists in unimaginable ways. So what happens when you hit this shell? It wouldn't be like crashing into a wall or burning up on re-entry. The forces here operate on a level so strange that our human minds struggle to grasp them. You might feel sudden, intense resistance, like hitting an invisible barrier that pushes back harder than any force you've ever experienced. But this is just the beginning. The quantum forces at work could tear at your very atoms, shredding the particles that make you up with pressures and energies beyond what our current physics can fully explain. You wouldn't be incinerated instantly, like in a supernova explosion. Instead, your body and ship might begin to disintegrate slowly, not through heat or fire, but through a quantum storm that rearranges matter at a fundamental level. But here's the strangest part. You wouldn't vanish. You wouldn't be erased. Instead, the information that makes up you, your atoms, your memories, your very essence, would be smeared across the Gravastars' shell. Like ink spread across a cosmic canvas, your physical being becomes frozen, trapped in time on this boundary. You would exist, but not as a living, breathing astronaut anymore. You'd become a record, a ghost trapped in the quantum fabric of this strange shell, held there indefinitely. In a way, you'd be stored, not deleted. And that's what makes Gravastars terrifying yet fascinating. They don't obliterate, they imprison. They preserve information in a state beyond life and death, beyond our classical understanding of time. To fall into a black hole is to be destroyed. To fall into a Gravastar is to be trapped, endlessly frozen in a cosmic limbo. This raises deep questions. What does it mean to exist if you're no longer alive, but your information is preserved? Could the Gravastars' shell be a kind of hard drive for the universe, storing the history of everything it ever swallowed? Are you just a fragment of data, a frozen echo locked away from time itself? Scientists still debate this. Gravastars push the limits of physics and philosophy alike. They challenge our understanding of reality, identity, and the ultimate fate of matter in the universe. So if you're unlucky enough to fall toward a Gravastar, don't expect the violent death of a black hole. Expect something stranger, a fate not of destruction, but of eternal imprisonment on the edge of cosmic mystery. Are black holes even real? This is where things get uncomfortable. Because the truth is, we've never actually seen a black hole. Not in the way we imagine. Not in the way science fiction loves to show us. A swirling void in space with a glowing ring of fire. We've seen the consequences, the warping of light, the X-ray flares from gas being ripped apart, the quiet disappearance of stars that got too close. We've even captured images, like that famous blurry photo of a shadow in the galaxy M87. But that wasn't the black hole itself. That was just its silhouette, a dent in the fabric of reality so deep, not even light could crawl out. But the black hole, the singularity, the actual object, no one has ever seen that. It's one of the strangest contradictions in modern science. Black holes are among the most studied, most modeled, and most talked about phenomena in astrophysics. And yet, they're also the most elusive. By definition, they cannot be observed directly. Everything we know about them comes from inference, from the behavior of light, matter, and energy near their edge. We call that the event horizon, the point of no return. The place where gravity becomes so strong, nothing escapes, not even information. And this presents a problem, a deep, philosophical one. Because if we can never observe what lies beyond the event horizon, if the interior of a black hole is forever cut off from our universe, how do we know it's real? How do we know we're not just projecting a theory onto the shadows? The idea of black holes was once considered absurd. Even Einstein himself doubted they could exist. His equations said they were possible, that if enough mass was crammed into a small enough space, space-time would collapse in on itself. But the idea that nature would allow such a monstrosity, a place where gravity becomes infinite, where does time literally stop? He thought it was too extreme to be real. But over time, the evidence began to pile up. In the centers of galaxies, something was causing stars to whip around at unimaginable speeds, something invisible, yet impossibly massive. In binary star systems, strange objects were consuming their partners, not with light, but with silence. And when two of these invisible beasts collided, they sent ripples through space-time itself, gravitational waves predicted by Einstein, and finally detected a century later. Still, a mystery remains, because while the math works and the predictions match what we observe, we're still dealing with an edge, a limit, a horizon we can never cross. Imagine standing on a beach, watching the ocean swallow the sun. You can see the light fade, you can feel the pull of the tide, but you'll never know what's happening beneath the surface. Not directly. That's how black holes work. We can see what they do, but not what they are. And what they are might not be what we think. Every time physicists push deeper into the nature of black holes, they run into paradoxes. Information should be destroyed in a black hole, but quantum mechanics says information can never be lost. The laws of physics break down at the singularity, a place where density becomes infinite, and the very equations we use to describe reality stop making sense. And yet, this singularity is supposed to exist right at the heart of every black hole. Something's not adding up, and this has led to an uncomfortable realization. Black holes aren't just astrophysical objects, they're questions we don't yet have the tools to answer. They force us to confront the limits of our understanding, the place where gravity and quantum physics collide and refuse to play nicely. They are the smoking gun of a theory we haven't discovered yet. And maybe that's why they feel more like myths than machines, like dragons in the sky, real in effect, but hidden in nature. We treat them as cosmic endpoints, the end of time, the end of matter, the ultimate gravitational collapse. But are they? Or are we missing something? When a massive star dies, it collapses. The core implodes. The outer layers are flung into space. And if the core is heavy enough, the collapse doesn't stop. It continues inward, compressing matter into a volume so tiny, so dense, that gravity overwhelms everything else. That's where we say, a black hole is born. But what does that even mean? At some point, matter stops being matter. Atoms break down. Nuclei dissolve. Even the quarks inside protons and neutrons get torn apart. And then, that's where the theories break down. It's the scientific equivalent of writing, "Here be monsters," at the edge of a map. And yet, we keep looking. We keep modeling. We keep trying to make sense of these invisible monsters. We give them names: stellar mass black holes, supermassive black holes, intermediate ones, primordial ones. We map their gravitational fields. We simulate the way they spin, the way they merge, the way they evaporate, very slowly, through Hawking radiation. But at the core of all this, there's still doubt, still mystery, still a very real possibility that what we think of as a black hole is just our best guess at something stranger. Think about it. The universe doesn't owe us clarity. It doesn't have to make sense in a way that's comfortable. Just because a theory fits doesn't mean it's the truth. It might just be a useful illusion. What if black holes are something else entirely? Not places, but processes. Not objects, but events. Not things that exist in space, but transformations of space itself. We often describe them as hungry, devouring light, eating matter, feasting on stars. But maybe they're not devouring anything. Maybe they're dissolving it, translating it, moving it into some form we can't yet comprehend. In a way, the black hole is the perfect symbol of our ignorance, a place we know exists, but can never touch, a question we know we need to ask, but may never answer. a shadow cast by a truth too deep to reach. And maybe that's okay. Maybe black holes aren't meant to be solved. Maybe they're meant to remind us of something deeper, that the universe isn't just vast, it's unknowable. And in that unknowability, there's beauty. Because when we stare into the darkness, hoping to find an answer, we're really just seeing the outline of our own curiosity, a shape in the void that reflects not what we know, but what we want to know. And the truth is, that's what science is all about. Not the answers, but the questions. And black holes? They're the biggest question mark of all. What if the Big Bang wasn't the beginning? We like to think of it as the ultimate origin story, the spark that lit up existence, the first moment when time, space, matter, and energy burst into being from nothing. It's the moment etched into every cosmology textbook, the sacred page, one of our universe's story. But what if it's not the whole story? What if the Big Bang wasn't the beginning, but an aftershock? There's a strange idea floating in the minds of some theoretical physicists. It starts with a different kind of cosmic monster, not a black hole, but something weirder, something called a gravastar. On the surface, a gravastar isn't all that different from a black hole. It forms from the collapse of a massive star, just like a black hole does. It warps space, bends time, exerts immense gravity, but it hides something curious inside. Not a singularity, but a core of dark energy, a kind of cosmic pressure cooker, a force that pushes out rather than pulling in. In a black hole, gravity wins. Everything collapses into a single, infinitely dense point, a singularity. But in a gravastar, something fights back. A strange form of vacuum energy fills the interior, resisting collapse. Think of it like a tug-of-war between gravity and this mysterious, repulsive force. For a while, they balance. The shell holds. The structure survives. But what if that balance breaks? That's where things get wild. If the shell of a gravastar were to rupture, even slightly, all that trapped energy could come rushing out. Not gradually, not gently, but explosively. It could be a cataclysm of such magnitude that it would dwarf anything we've ever observed. Not just a supernova, not just a gamma-ray burst, but something much, much bigger, something that could tear apart the very fabric of space and time around it. And here's the crazy part. Some physicists wonder if that's exactly what the Big Bang was. Not a spontaneous creation out of pure nothingness, but a death event, a rebound, the final gasp of some massive gravastar, collapsing inward, crossing some critical threshold, and then exploding outward with enough energy to create an entire universe, our universe. Let that sink in for a second. The birth of everything we know, galaxies, atoms, planets, people, might not have been a beginning at all. It could have been an ending. The last breath of a universe-sized object in another cosmos, folding in on itself and then breaking open in a moment of pure release. From death, birth. This flips everything we think we know on its head. Because the Big Bang has always been wrapped in mystery. We can describe what happened after the bang, down to the tiniest fraction of a second. We know how the universe expanded, cooled, formed structure. But that first instant, the bang itself, it's still hidden, still behind the curtain. Physicists call it a singularity, but really that's just code for we don't know. The math breaks down. The laws of physics stop working. Time becomes undefined. In that tiny moment, everything we understand about how the universe operates just falls apart. But a gravastar changes the equation. Because if the Big Bang wasn't an origin, but a transition from one kind of structure to another, then maybe the singularity never happened. Maybe there was no infinite point, no boundary, just a phase change. One state of the cosmos giving way to another. Maybe what we think of as the beginning is just a ripple from a deeper layer of reality. Imagine a star so massive it collapses not into a singularity, but into a bubble of trapped vacuum energy. Imagine that bubble growing unstable. The tension builds, the shell strains, and then, pop, not in the sense of a balloon, but in the sense of a rebirth, a reconfiguration of reality. Inside that rupture, space and time stretch and swirl, temperatures skyrocket, particles form, light flashes into being, and in an instant, a universe is born, not within the shell, but from the shell, expanding outward from that tear, like ink swirling in water. That might sound like science fiction, and to be clear, it's still just a hypothesis. We have no direct evidence for Gravastars, no confirmed sightings. But then again, for most of the 20th century, black holes were just a theory too. Einstein himself didn't believe they were real. He thought nature would find a way to avoid such absurdities. And yet, here we are. We've taken pictures of the shadows cast by black holes. We've listened to their collisions echo across space in gravitational waves. The universe is full of things we once dismissed as fantasy. Gravastars could be next, and if they are real, and if one of them really did rupture to become our cosmos, then everything changes. The story of our universe becomes just one chapter in a longer tale, a tale of cycles, deaths, and rebirths, cosmic structures forming, failing, and spawning new realities in their wake. It raises wild questions. If our universe came from a gravastar, what came before it? Was there another universe? A star that collapsed inside that one and birthed this one? Could we be part of an endless lineage, a family tree of universes, each born from the remnants of the last? And what happens next? Could our universe too, one day collapse into a gravastar-like object? Could it end not in heat death or a crunch, but in a transformation? Could the cycle continue, endlessly rebirthing itself through these strange, energetic cocoons? We don't know. We may never know. But what's clear is this. The Big Bang may not be the final answer. It may be a clue, a signpost, a doorway into something deeper, stranger, more intricate than we ever imagined. And in a way, that's beautiful, because it means the cosmos isn't just a one-time miracle. It's a living, evolving thing, a place where even endings can be beginnings, where death is never just destruction, but the first step in creating something new. Maybe that's what we are, echoes from another world, children of a cosmic collapse. And if that's true, then perhaps we've only just begun to understand what kind of universe we really live in. Gravastars, the gravitational vacuum star. Gravastars aren't just a cooler version of black holes. Imagine standing at the edge of a mystery we've been circling for over a century. Black holes, these cosmic monsters that eat light, bend time, and sit at the hearts of galaxies, have long fascinated and terrified us. We've built theories around them, simulated them, even tried to photograph them. But here's the uncomfortable truth. What we think of as a black hole might not be real, not in the way we imagined, and that's where gravastars come in. A gravastar, short for gravitational vacuum star, and is not just a quirky alternative to a black hole. It's a completely different answer to the question we've been asking since Einstein. What happens when gravity goes to its absolute extreme? See, black holes present a kind of failure in physics. They predict a singularity, a point of infinite density where space, time, and the known laws of nature break down. And here's the thing. When a theory gives you an infinity, it's usually a sign that something's wrong. It means the math has hit a wall, that we're missing something deeper. That something deeper might be gravastars. If gravastars are real, they fix the singularity problem. They remove the idea of a place where physics collapses and replace it with a new structure, one that obeys the rules, or maybe even rewrites them in a more elegant way. Instead of a singularity, you get a strange vacuum-like core surrounded by an ultra-dense shell. No tearing of space-time, no mathematical infinities, just a radically different object that looks, from the outside, almost exactly like a black hole, but is something else entirely on the inside. And that changes everything. We should care about gravastars, not just because they're a cool new theory, but because they might solve the deepest paradoxes we face in modern physics. Take the information paradox. According to quantum mechanics, information about particles, states, energy can't just disappear. It's one of the most sacred laws of the quantum world. But black holes, they eat information and never seem to give it back. That's a problem. Hawking radiation suggests black holes evaporate over time, and if all the information they swallowed vanishes with them, that breaks the rules of quantum theory. It's like the universe just shredded the script and walked off stage. Gravastars offer a way out of that nightmare. If there's no singularity, no true point of no return, then maybe the information isn't lost at all. Maybe it's stored in the Gravastars shell, or reflected somehow, or encoded in ways we don't yet understand. But it's there, preserved, hidden in plain sight. That's not just a fix to a physics problem. It's a whisper from the universe saying, I make sense, you just haven't figured out how yet. And then there's the quantum angle. Gravity has always been the odd one out. Electromagnetism, the weak force, the strong force, all of them play nice with quantum mechanics. But gravity, it resists. Einstein's smooth, continuous curves of space-time don't fit cleanly with the jittery, probabilistic world of quanta. It's like trying to fit a vinyl record into a streaming app. Something's got to give. Physicists have spent decades trying to unify these worlds into a theory of everything. String theory, loop quantum gravity, holographic principles. None have fully succeeded. But gravastars? They might be the meeting point. They could be what happens when quantum pressure pushes back against the collapse of a star, creating not a black hole, but something new. Something born from the marriage of Einstein's curvature and quantum mechanics' weirdness. If true, that's seismic, because it means our universe isn't just a chaotic mess barely held together. It's structured, intelligently, precisely. The laws aren't colliding, they're collaborating. And let's be honest, there's something unsettling about the idea that nature would allow singularities to exist at all. These places where time ends, space breaks, and the laws of physics literally don't work? That feels more like a bug in the system than a feature. Gravastars flip the script. They suggest the universe doesn't like breaking its own rules. It bends them, stretches them, reconfigures them, but it doesn't snap. There's a quiet elegance in that. Even more strangely, gravastars might not just be replacements for black holes. They might point to an entirely new phase of matter, a new way the universe stores energy and structure. What if gravastars are just the first hint? What if there are other exotic objects out there, things we haven't even dreamed of yet, that obey the same deeper logic? There's also something poetic about what gravastars represent. They're born from death, like black holes. But instead of collapsing into oblivion, they stabilize into something new, something strange, maybe even something eternal. In a way, gravastars tell a more hopeful story, one where destruction doesn't mean erasure, where even the end of a star leads to a second act. We care because these aren't just abstract ideas. They touch the core of what we believe about reality, about death, about the fate of the universe. If black holes aren't what we thought, then what else isn't? What other assumptions have we made that might be beautifully wrong? Science isn't just about collecting data and crunching equations. It's a form of storytelling, a way of understanding our place in the cosmos. For decades, black holes have been the main characters in one of our greatest scientific epics. But maybe they were red herrings. Maybe the real story is stranger, subtler, more surprising. Maybe the universe has been hiding its secrets in plain sight. If gravastars exist, they're a clue, a breadcrumb, a signpost pointing toward the next revolution in physics. And not just in a new theory kind of way, but in the deepest sense possible. A shift in how we think about space, time, matter, and reality itself. The kind of shift that happens once a century. The kind that opens doors we didn't even know were there. And isn't that why we're drawn to science in the first place? Not for the answers, but for the moments that make us question everything. That pull back the curtain just enough to show us there's more. more mystery, more wonder, more beauty. Gravastars remind us that the universe still has surprises left, that the story isn't over, that maybe, just maybe, the best part hasn't even begun. So maybe black holes were never the final answer. Maybe they were just the prologue to a much stranger story. For decades, we've stared into that darkness, convinced we were looking at the end, the death of light, of matter, of meaning. But what if that darkness was only a mask, a shell around something deeper? Not a void, but a vessel. Not a grave, but a gate. Because that's what Gravastars suggest, that the universe doesn't destroy its secrets, it hides them. It tucks them away in the quietest corners of space, behind layers of pressure and quantum strangeness, waiting for us to look closer, to ask better questions. Maybe what we've been calling black holes are really vaults of cosmic memory, where the laws of physics don't break, but bend with grace, where light doesn't die, it disappears until we're ready to understand why. And that changes everything. It means the universe is more than just chaos and collapse. It's clever, it's careful, it's building things we're only just beginning to notice. The Gravastar might not just be another theory, it might be a clue, left for us in the fabric of reality itself. A reminder that even in the darkest places, the story isn't over. Well, if you found this journey mind-boggling, drop a comment below and share what fascinates you the most about the topic. And if you haven't already, don't forget to like the video and subscribe to the channel so you don't miss out on our next deep dive into the mysteries of the universe. Thanks for watching, and keep questioning everything, because the universe is far stranger than we can imagine.